Oh my god. I'm so sorry, guys. Testing the chat. Okay, chat works. I'm so sorry, guys, because stream just stopped. It's a pity. Yeah, it's a pity. I don't know why the connection just dropped. I'm so sorry. Let me also post it in Telegram, because what the hell is this? Yeah, just connecting it here. So I don't know what happened. I just lost connection and my stream just stopped working. Very bad. I don't know how to overcome this, in the sense that to not create new stream, because yeah, previous stream just interrupted. It was done, kinda, and the only thing I know I can do is to just start new stream, right? But I will lose pretty much all people that were watching me. So I'm not quite sure about this. Anyway, what we're gonna do now, according to our schedule, is we're gonna do system design. So now, where is Miro? Oh my god, what the hell? Why nothing is working for me today? I don't understand this. So yeah, this guy is done. Enough LeetCode for today. Now I can have some AWS interview screening feedback. So yeah, I had AWS screening interview. This is the online assessment that you are getting before you have interview with real people. So it's either interview loop with system design, algos, behavioral question, and so on. This 4 or 5 hours interview, or before some pre-screening, which is not interview loop, so not full cycle, not 4 or 5 hours of interviews, but maybe 1 or 2 interviews with hiring manager or some engineer that will test your basic skills related to troubleshooting, related to your maybe system design as well, some general questions and stuff like that. So this is usually how it works. Still not all audience has joined. I don't know. I don't know what to do. I don't know even what was the problem. Was it the internet connection in Microsoft Office? Can it be the problem? I don't even know. Can it be this interruption? Maybe it can. Anyway, I'm gonna prepare myself one more glass of water. So I will just leave this message and disappear for 1 second. Okay, there will not be any more breaks. So yeah, let's go, people. Unfortunately, I lost all of you guys. We had around 10 to 15 people, which was very unusual for my streams actually. So AWS interview screening. Actually, they had now this confidential stuff that I'm actually not eligible to reveal what I was asked about, so I will not. But I can give you some interesting task, so you can just think about this task and how you would solve it. Overall, I got two interview questions, which I would say they were medium LeetCode problems and 1.5 hours to solve them. I saw all of them. The problem is that both of them were solved in the way that they were hitting time limit exceeded. I don't know whether it was problem with JS and my solution. Actually, with my solution. So first problem, I just didn't come up with better complexity. And second solution, I just overall solved it in a very weird way. That I don't think this was the right solution that interviewer would expect me to have, but it was working, so it passed all the test cases and also hit time limit exceeded. And my optimization somehow didn't work on some big input data that actually I have no idea why, because I couldn't even print it out because it's too large, right? So I might give you maybe some interesting problems and you just think about them. They are not related to AWS interview. Yeah, I will say like they are not related to AWS interview. So interesting problem here is, let's say you have box with apples. Yes, JavaScript, thank you. You have box with apples, and you have you and your friend. Please do, oh my god, function task. Okay, I hope it will be better now. So let's say you have box with apples, and this box has some amount of apples. Let's name it size. With size apples inside. In your task, you have you and your friend, and both you and your friend can take some defined amount of apples in one go. So you can take X apples from box in one go. Your friend can take Y apples from box in one go. This is the task. It was actually much more complicated, but no, it wasn't. It's just some random task. Sorry, it wasn't complicated. I'm just talking about some task that I came up on my own. So you made a bet with your friend that if you're gonna finish the box, which means that you're gonna get the last apples, which make the box empty, you will win and your friend will give you $1. Right? Now, yes, I would put it like that. So your task is actually to ensure that during your go, the box will become empty. This is your task. You are starting, so you first are taking the first move and taking X apples from the box, so from the size. Your amount, friends amount. So you are starting, it's your turn, and then it's your friend's turn, and your friend's turn. Let me give you some examples. Let's say you have 5 apples and you can take 2 apples. Your friend you can take 2 apples. Friend can take 3 apples. In this case, since your turn is the first, you're taking 2 apples. It becomes 5 minus 2 equals 3. Then it's turn of your friend. He gets 3 apples. 3 minus 3 equals 0. He was the last one who got the last apples from the box. So you don't get your dollar. Now there is one more thing in this task. You can ask your friend to skip his turn. So in this case, in this specific example, you have 5 apples, you're taking 2 of them. It's 5 minus 2 equals 3. Now, you know, if your friend is taking 3 apples, you're gonna have 0, he will empty the box, you lost. So you're asking him to let you go. So it's your turn again. You're doing 3 minus 2 equals 1. Now it's again turn of the friend. And basically he will get the last 1 apple because he can take 3. So you're asking him to skip again, and you're taking 1 minus 2 equals minus 1. These were your last apples. Basically you should come up with constant time. Oh, sorry. You should come up with the constant time solution. How to calculate how many skips you should ask for the friend in order to take the last apples and to get your dollar. So your task is to return how many times you should ask your friend to skip turn. It can be 0. It for sure can be 0 because well, let me draw you an example when it will be 0. Let's say let's say if it was 4 apples, which is size, and then you can take 1 and your friend can take 2. So in this case it will be 4 minus 1 because your turn equals 3. Now your friend is taking 3 minus 2 equals 1. Now your turn 1 minus 1 is going to be equal to 0. You should return 0 skips because you don't have to ask your friend. You're gonna get the last apples. Another case is this one when you need to ask your friend to skip 2 turns. And you should implement some kind of formula which will run in constant time to understand how many skips do you have. So this is just random task that I came up. Yes, this is what I will tell, and some another task I didn't come up with yet, so there will not be any tasks anymore. Just if you're interested and paying attention enough, you will get what you should get. Now system design, URL shortener. Let's finish this thing eventually. So I think I'm gonna drop some of these guys completely because I'm tired of this mess over here. What is this? Is also complete. bullshit. This is for my video, it's okay, let it be here, no problem. Now, yes, this scheme, well, we will rewrite it. Yeah, this is, again, we don't have to. Good, this is for snowflake. Break, we don't care. Good. Yeah, pretty short and good one. So, URL shortener. As you remember, one of our approaches that is going to work is that we are getting some unique key, which is number key with the, oh my god, is this drop again? I hope it's not drop. Oh my god. Very unstable connection or whatever it is. No, seems like it's working, hopefully. So, this is our approach. We should get some unique key, some number, which we're going to take from Snowflake auto-increment scalable solution for unique ID. This way we are getting unique numbered ID with the size 64 bits. And we're going to convert it to base 62, which gives us exactly the safe characters in URL that you can put safely and you will not break anything. And this is probably one of the smallest things we can do. How many URLs in this case can be created for us? So yeah, let me do mass. So 2 to the power of 64, or it's 60, like how many? I don't remember what is. Let's even assume it's 62 bits. How big the number is? So pretty big, yeah. I don't know the representation. Oh my god. Can you do decimal? Okay, I have to ask ChatGPT because I don't really remember how to. Too big number. Okay. Or otherwise, what is the long max number? Long, so I guess how many bits? I'm interested in bits. Bytes. Oh my god. So this is the number, or like pretty big number, right? So this is how many unique short URLs we will be able to theoretically create. It will not be that great number because it depends on the timestamp, right? Do you remember? Yeah, I hope you remember how our Snowflake thing works. That actually our Snowflake ID, which is unique auto-incremented scalable distributed solution for unique key generation, unique number generation, which works pretty much like first versions of unique universal IDs, so GUID or UUID, whatever you call it. So the first, I think 40 something bits is time. So these bits are reserved for time. Some bits are reserved for machine ID, and some bits are reserved for sequence number. So the thing is that we never can for sure start from the time 0. We have to have some epoch which is like starting point, same like in Unix timestamp, which starts from 1970, but let's say our epoch can be 2025 today, right? And we for sure will start, our service will not start from 0 milliseconds, it will start, I don't know, from like some millions of milliseconds maybe. So that's why some of these numbers will be lost, but overall, this is pretty big number, right? What is the 2 to the power of 64 bits number? So 64 bits, it means the binary representation. Yeah, and this is exactly how big the number can be. So it is yeah. So these are millions, billions, trillions, and the rest I don't know even how it's called, to be honest, in real world scenario. So pretty big number of unique IDs we can generate, right? Even if it's even if it's I don't know how big load it can be in our system design to support. So let's say we have millions of unique millions of new URL short URLs requested. So let's say we have 1 million, this guy gonna be removed, 1 million per second. These are requests for short URLs. Requests for short URL. In this case, we're gonna return 1 million unique IDs per second. So in 1 minute, it's gonna be 60 millions per minute, and per hour, it's gonna be again times 360 million per hour, and per day, oh my god, so I'm gonna be times 24. So these are millions, so it's gonna be 8 billions per day. So in case we have 1 million requests per second, which is not quite true, I'm pretty much sure it's not possible. What co-working space you're in? I'm in the Microsoft Office at the moment. So yeah, this is Sunday, there are no people, and this is my actual workplace here, that I will be here tomorrow on Monday, working on my usual stuff at Microsoft. What country are you in right now, sir? I'm in Czech Republic. Yeah, Czech Republic at the moment. So 8 billion daily new URLs created, and if we even try to delete this number by 8,111, 111, 111, is it billion? I'm a bit lost. It should be billion, right? So let's just try to understand how many days we will be able to issue new URLs in our URL shortener. This is the number of days, right? And now let's just, if these are days, let's divide it by 3. Okay. 65. So pretty much this is the number of years we're gonna issue new URL, new short URL in our system design if we are using this approach. So it's gonna be 6 million years our service will be operable, which means in this case, like after 6 million years, I guess some of the URLs will be outdated already. I hope. So behind our math, we should be good with even requesting 1 million short URLs per second. It should be quite good. Even 10 million, we're still good. We will not run out of our unique numbers. Okay, are you teleworking in America via remote work, or you work for multinational org? I don't really get your question. So our team at Microsoft, we are one backend part of the Teams/Outlook application. So basically M365, we are not specifically tied to Teams. Yeah, so my team is responsible for presence, which is online, offline status in the Teams, Outlook, Skype. Skype is that already, but before it was. And yeah, our team is based on Prague, so we don't have peers like our direct colleagues in USA. Yeah. So I don't know how whether I answered your question or not. Hope I did. Yeah, so from the mass standpoint, it should be okay. From the capacity, we always can scale, right? We always can scale. So it shouldn't be a problem. The main thing that logically, at least, we will not run out of our short URLs, which is pretty cool. Now, let's design a high-level architecture, how it's gonna work. So we have our maybe not. Let's do it this way. So we have write flow, and we're gonna have read flow. In write flow, so we have, we have our input somewhere here. This is the REST API. Let's say URL shortener. This is some RESTful endpoint, whatever. And this guy is accepting requests from customers. Hey, create me a short URL that will point to URL X. So this is exactly what we're gonna. Shit, I think I don't need this guy anymore. Let me just leave a couple of them. Yeah, too many. Okay, and this guy's removing here. Okay, so this endpoint is exactly going to be responsible for this. So any customer or client goes and tells, give me short URL X that will redirect me to my URL Y. Kinda, this is what this endpoint will be responsible for. And in this case, in high-level overview, what we're gonna do, we're gonna request unique ID generator. So we are sending our request from this big guy here. This is completely, as we already designed during last stream, it is completely stateless, so it returns us 2 to 64 bits number. Now is this number, what we are doing, we are converting it to base 62, and then okay, we have this guy, and we inserting it to some kind of storage. Now the actual system design starts. So what storage we're gonna choose? What storage we're gonna choose? So let's maybe start with pretty cold storage, which is some database, right? Whatever. For now, it's only one database. We'll scale things out later. We write this short URL here in DB. Caching latency will be covered also later. We write this guy to database and return, after we wrote it, we return this short URL to the customer. Return URL Y. Oh, sorry, URL X. This is X. Right, and right after that, what we want to do, in case our customer goes to our service, read flow exactly, redirect me to URL Y. Hey, this is my URL X, redirect me. So in this case, unique ID generator is not involved anymore. What we are doing, we are getting URL X, we look up in the DB, we're returning URL Y, and we are doing redirect 302. That should be actually is. That should be is. This is very high level architecture. We're gonna design it a bit deeper now. We will not cover unique ID generator because this is just a bunch of computes. They're completely stateless. They are not even interesting to design. Let's focus on the like a bit lower level. So how our URL shortener should be to handle. Let's say in our case, we're gonna have. Oh my God, we're gonna have 1 to 10. Write to read. So in case we want to support 1 million writes, it means we're gonna support 10 million reads. So for sure one single machine cannot handle this, of course. How it's gonna be working now? So let's go here. Of course, since this is compute, we are starting with load balancer. We'll have a bunch of load balancers, and how it will be working, that we're gonna chain these load balancers through the DNS straight away. So DNS can return it in round robin manner, whatever. Yes, so actually I want to do this. Yes, so we have n load balancers. Like that. Or like this, I don't know. Yeah, and we have, I don't know, some DNS. We don't control it. I think DNS is also quite different problem to handle. But let's say we have some DNS, which is external service. And in round robin, it resolves us domain and it resolves IPs to these load balancers. So this is the client. I don't know, some mobile, whatever. It goes to these load balancers, and load balancer is resolved. Okay, it goes to DNS actually, and it resolves one of the load balancers. Good. This is how the load balancers are resolved. Now, every of these load balancers, they are actually let me do. They know about our RESTful APIs, so we can scale them as well. So there is actually a layer of, let's say, URL shortener. I guess maybe we can split read and write services completely, so the application deployed as URL shortener for write can be quite different from the one deployed for read, but actually, yeah, let's think about it, whether we need it or not. So we have a bunch of URL shorteners. It will be more of them than LB. Every single one of them is exposing exactly the same write API endpoint here. So this we sorted out, and load balancers know how to speak to them. Okay, then just like that. They know how to speak to them. Actually, let me also draw just two for simplicity. So this load balancer knows about 2 of them, and this guy knows about 2 of them as well. And based on the availability, they will send request to the one who is alive at the moment. Now, URL shortener, they both communicate with this unique generator, which is completely external service, so it is scaled on its own. We don't have control over it. We assume it's going to be healthy up and running. In case no, we have retry. If retry doesn't help, well, we should return some 500 or some error to our customer, like try next time. Now, when we just requested this 264 bits number, URL shortener is creating the base 62 representation of the URL part, URL path basically. And we are putting this path to database. So there's going to be database. Let's say some SQL or not SQL. What do we need actually? It shouldn't be that complicated, to be honest. So what it should be, what mapping actually we do need. So database mapping going to be, so for sure we want mapping from the short URL SQL table. Let's say we want to have short URL that is result to customers URL. This is just 2 fields in the table, right? Do we need customers URL? Well, most probably we do need, but we don't need it in terms of our read flow, because for read flow we're gonna just work with short URL. If short URL doesn't exist, bye-bye. Like, sorry, we cannot find your URL. The mapping vice versa can be represented for customer user profile, which is not gonna be something that hard. We can implement and think about it later. But for now, yeah, this is just simple table. And I actually guess maybe we don't need to have it in our table. Actually, I would rather put it into the cache. But we need to ensure durability, right? So first I'm putting it to my SQL database, and then I'm putting it to the cache. The URL mapping, let's say, is not changing. It can be changed, but it will be propagated with the eventual consistency most probably. So I would put, okay, let me name this guy as DB. And this is what's gonna be in this DB. Basically, yeah, 2 fields. That's it. It is pretty much enough for the needs we need. Yeah. And also I'm putting this guy to cache. Let's say I have some distributed cache like Redis, maybe, I don't know. And Redis also gonna have exactly same thing for now. So if somehow from Redis it disappears, so we don't care. In this case, we can just, you know, fall back to our database and ensure durability. And we are writing it firstly to database, then to cache. Writing to cache can fail, we don't care. Writing to database cannot fail. Now, we have pretty much scaled computes and load balancers with DNS and this guy, but we still have to scale our database. Hi bro, how's it going? Very cool, very cool. I got some stream dropped a bit, but overall it's cool. So now we need to scale our database in cache. So how we are doing that? Let me actually remove it. Can I just take it a bit lower? Yes. So how we are doing it? Since we have only 1 million writes per second, do we need to have anything else than just regular master leader replication? This is the question. Can we handle? I think we can. So how a database is gonna work? We're gonna have partitions. So this is partition 1, this is partition 2. Yes. Let me then write. And based on what? We're gonna partition by short URL. So partition key gonna be hash short URL. This is our partition key. This is how we're gonna look up where is particular database. We can apply something like consistent hashing or rendezvous hashing, doesn't matter, to be able to shift the data, and we can use something that Redis is using, right? Anyway, there should be something maybe already implemented for this specific type of database, but let's say that for now it's okay, right? For sure, we are putting index on the short URL because in case there is cache miss, we want to look up this data pretty fast. Good. And for sure, since it's gonna be available, we're gonna create replica. Oh, sorry. So we're gonna create replica. Exactly. And this replica gonna use just async replication. Sync. Just like that. Exactly same thing happens to second partition and all other partitions as well. So this is gonna be a replica 2. I don't know whether we need more replicas. We can do more replicas in case we are afraid that, you know. But for now it's leader follower. So it's gonna perform leader election in case primary is down, right? And let's say we allow read and writes from this guy. Why? It depends which level of consistency we want to have, because actually I would assume once customer entered the URL and we return this URL to customer, once he followed, he shouldn't get not found, right? He should go and get the real URL, and he can get not found in case we are allowing reads from replica and writes from to primary. In this case, if we write to db1 and returned to customer the URL, but replication lag is, let's say, half a minute, some GC pause, whatever happened, customer will go here and he will not find this URL, unfortunately. Cool. So this is about the database replication. Should pretty much handle everything. Anyway, the database is not going to be read heavy. It's going to be write heavy, because in our setup, our read request should go to cache and write request as well. So cache is the, I would say, weak point in this case, right? Yes. So cache, in this case, cache gonna have exactly same strategy. So this is cache partition 1, cache partition 2. There is also replication, replica 1, please, replica 2. Exactly same thing. And in this case, actually, it might be a good idea for creating more than one replica, but not for high availability purposes, but for the purpose of read load spreading, because since our cache will be extremely read heavy, so first request gonna hit cache when we try to resolve the URL. Since it's extremely read heavy, we might spread these reads not only on partition level, but also on the level of replication, and then adjust the settings, right? Yes, and that's basically it. And on the read flow, how it's going to happen, on the read flow, we're going to have exactly same thing. On read flow, we're going to have exactly same thing. But we are not writing here, so let me remove bunch of stuff. So when we hit the read, we exactly go same load balancers, URL shortener. We don't go to the unique ID generator at the moment. Then on URL shortener, since we got URL X, which is our short URL, first time we go to our cache, we are using exactly same hashing to understand the sharding ID or sharding key. So it's going to be short URL, which will give us some partition ID, and by this partition ID, we're going straight away to this partition ID, resolving it somewhere like, I don't know, it lays somewhere in configuration, whatever. And we are trying to read from the replica or from the cache, whatever, from any instance. If we cannot resolve, we fall back. So we can actually fall back to database. If there is not found, fall back. And if nothing is found, we just return 404. Or if there is URL found, we're resolving customer's URL, and we returning, we're returning 304, which is redirect, right? Redirect HTTP. Is it 302? Sorry, and 304. What is it? Is it a thing at all? Not modified. No, it should be 301. Yeah, let's say we return 301, whatever. 301 and redirect. Or let's say we have 404, maybe for user interface, UX, UI purposes, we can still redirect to some default page, whatever, or serve this page from somewhere, doesn't matter. Yeah, so actually URL shortener is not that big of a deal once we have basically the unique ID. We for sure can see that how it's gonna work. And once we can ensure uniqueness of short URL, there is no challenge anymore. So we just apply regular patterns. Okay, we replicate the computes. Okay, we shard and replicate databases, async replication, since yeah, we can afford some replication lag, blah blah blah, no strong consistency. That's basically it. That's basically it. I don't know about follow-ups, what we should do here, but that's it. That's it, guys. I don't know, we can actually implement it, or maybe we can watch some implementations, real shortener system design, and actually check them from my perspective. So yeah, it can be a part of stream which can be named software engineer from Microsoft reviews system design live. I don't know, let's just try this approach, and also check our solution exactly and see whether we can modify it. But from my perspective, it should work. It should pretty much work. So we have our teeny URL. Okay, I was watching it some time ago, I guess. Let's check how it is approached.
Would be looking to be solved. So with that said, let's jump straight into it. So for the functional requirements, it's really simple. When we're given a long URL, we have to create a short URL, and then when we're given a short URL, we have to redirect the user to the long URL. And for the here. Then for the schema, again, really simple. We'll have a long URL, which will be a string, a short URL, which will be a string, and then a create that which will be a timestamp in URLs per second. So then we know that every year, so if we multiply 1,000 times 60 seconds.
Only 1,000 URLs generated per second. Well, not that. Yeah, we had much bigger value.
60 minutes times 24 hours times 365 days. Now we're going to be required to have roughly 3.5 billion or 31 billion URLs created each year. And then if we anticipate a kind of read to write request ratio of 10 to 1, that means we're going to be doing roughly 300 billion reads per year. So again, it kind of is something to keep in mind when interviewers, and it's fairly safe to assume that we'll be able to use A to Z lowercase, A to Z uppercase.
Yeah, exactly the reason why we're using base 62, because yeah, we want to use safe characters in URLs. So for example, we don't want to use question mark, we don't want to use hashtag symbol and stuff like that, because otherwise URL will be misread and it will lead to some unexisting thing.
And 0 to 9, and that means then we'll have a total of 62 characters to use. So then with that information, we can then look at how many unique short URLs can be created. So if we've got one character, if we put that to the power of 62, that means we'll have 62 unique combinations, which makes sense because there's only 62 characters to choose from. And then similarly 2 to the power, so we've used 2 characters, then we've got 2 to the power of 62, which is 3,800. And so if we skip on down to 6 to the power of 62, so for 6 characters we've got 56 billion, and then similarly it means then we'll have a total of 62 characters to use. So then with that information, we can then look at how many unique short URLs can be created. So if we've got one character, if we put that to the power of 62, that means we'll have 62 unique combinations, which makes sense because there's only 62 characters to choose from. And then similarly 2 to the power, so we've used 2 characters, then we've got 2 to the power of 62, which is 3,800. And so if we skip on down to 6 to the power of 62, so for 6 characters we've got 56 billion, and then for 7 we've got 7 characters we've got 3.5 trillion. And so if you look here, if we've got if we're going to be expected to generate 31.5 billion URLs each year, if we look over the span of 10 years, well, that's maybe 300 billion. And so you can see here, well, 56 billion won't kind of it won't be enough, but 7 characters at 3.5 trillion will be. So that's why we're going to go with 7 characters. Okay, so now that we have all the information we need from the interview.
Okay, he actually he thinks from different directions. So in our case, we already kind of where is my system design? What the hell? Where am I? Okay, in our case, we already realized that we want to ensure uniqueness, and we want to create our short URL from one pass. So in case we don't want actually to check whether this short URL that we just created using randomness or whatever, that we don't want to check it every single time. So that's why we chose the number approach, and number approach is the following, that we are going to have this amount of bits for our number, which is quite big value. It's not even billions, it's not even trillions, it's more than trillions. And now, then this value is going to be converted to base 62. Which actually it's just converting from one scheme to another scheme. So it was binary, so this number is, let's say this is x, it's binary, and this guy y should be 264 or 62. Okay, but math is understandable. In our case, we just don't have to do math over how many unique URLs we can generate from this 62 stuff, because we for sure know once we have unique number, we can convert it to unique base 62 URL, which will give us basically unique URL. We don't have to do over like this mass.
Kind of start putting together a really simple, high-level system design. So here we've got a user, makes a request to a load balancer, that will then distribute it to a web server, and the web server will then get the information it needs from the database and then redirect the user to the long URL.
Okay.
And the web server will then
Count cache. What is count cache?
he talked about. So the first naive solution could be to introduce a count cache, which means that every time a web server is given a long URL, it goes to the count cache and it asks for a number. The count cache will then return a number, base 10 number, and the web server will then convert that into a base 62, which will then be used as the short URL. And so while this technically works,
So this is exactly this is kind of approach we used. So you're getting the number, and from number you convert to base 62, and count cache kind of it is used here because it's kind of ensure to create unique number every single time, because for cache you can use atomic increment, and this will ensure uniqueness of your number and therefore uniqueness of your URL.
works. We've introduced a single point of failure here with the count cache, which is something we never want to do, and so we've kind of got to come up with a more nuanced solution. So here what we've done is we've horizontally scaled both the web servers and the count cache so that we've got multiple instances of each so that we can handle.
Nice. And how do you scale count cache? Because like count cache is stateful thing, so how you ensure uniqueness in this case?
If certain nodes go down. However, now we've introduced a new problem. So let's say, for instance, one of the web servers makes a request to the count cache and it gives back a value of 10, and then simultaneously another web server makes a request to the count cache and it also gives a value of 10. Well, then now we've got a collision, and this is something that we cannot have in our system. We want it to be kind of highly available, so what we're going to do now is we're going to move it on to the next level.
Well, it's collision is not problem of availability. You're still going to be available. The system will not be correct. The correctness is the problem here.
Okay, so looking at this next iteration, what we're going to introduce now is we're going to get rid of our count cache and we're going to introduce a zookeeper. And so zookeeper is really good to be used as a kind of centralized service for maintaining, configuration information and kind of providing distributed synchronization. And so we're going to use a range technique here. So what will happen is
technically, usually it's not a good idea to use the name of specific technology, especially if you don't know how this technology works, because if I would be the interviewer, I will straight away ask, even if I knew how Zookeeper works, I would ask all the questions that I would ask for this count cache. So how it works, how it's not the single point of failure, how it ensures, and like blah blah blah. So you just shift the questions from one square to another square, and usually my personal advice, I would say, for interviews, never rely on the technology name that it's somehow gonna help you or solve your problem with understanding or with solving technical challenge, because most probably interviewer will ask you, okay, how this technology works and how this technology solves this challenge, how you can ensure that these challenges will be solved with using of this technology.
Range of values from which it can create URLs. And so, for instance, the first web server might come over and it'll give it the range of 0 to 1 million, and the next range will then be 1 million to 1 million and 1 to 2 million. So what this means is that each server will be creating unique short URLs as they're all operating in different ranges. And so when a new web server comes on, it'll reach out to the Zookeeper and it will then ask, okay, what ranges can I have? And it'll give it a new range. And then similarly, when a web server completes its range, it will then reach out to Zookeeper, which will then provide us a new unused range. And then you may be
you know what is the problem here? Everybody who is in the chat, let's actually review. I like to review somebody else's design. This is very funny. So what is the problem with this approach? This is the something called ticket server approach. I don't know. Ticket server approach, particularly context to issue tickets. No. range of numbers. Maybe this is how it will be used. I know that I want to have the number of technology. Oh, sorry, name of technology. So because there is a big problem with this approach, actually, big problem. So how it's called? Oh yeah, ticket servers, but this is different stuff. Yeah, this is different stuff. Not this ticket server. Okay, whatever. So the approach that is suggested in this system design, that actually there is Zookeeper. Okay, first of all, the interviewer will straight away asks you how. Okay, if you think it's consistent, right? So you must probably tolerate availability. So how it is not a single point of failure. If it's not and it has different instances, okay, how is it consistent? How we ensure that situation when two web servers kind of get to two different Zookeeper instances and they are not getting the same sequence, for example. How we're going to ensure this? So this is what good interviewer will ask you straight away. This is the first problem. Second problem. Okay, let's say I will even draw this. So let's say we have our Zookeeper. Let's say it's even a single instance, doesn't matter. Let's say there is one server who asks for 0 to 1000, let's say. There is another server that asks from 1001 to 2000. And these are IDs, these are sequences that our server is going to operate and provide using these numbers to generate the short URLs. Now the problem. With doing that, we are actually putting our servers, which are stateless by default, to a stateful mode. So now if your server is down, how are we going to ensure? So this server was processing some numbers and now it is 1533 IDs were generated from 2000. How are we going to ensure that after this server is alive, it will exactly start from this point? Okay, we're going to write to some file, whatever. How are we going to ensure that write happened? Like, there is a bunch of problems that arrive when you put state into the server instead of having it like out. Okay.
Asking, well, okay, well, what if a web server reaches out to Zookeeper? It's given a range, but then it instantly dies. Well, what that happens
Okay,
with that
good. Sorry, this is exactly the problem I described, and let's hear what is the solution.
Range will no longer be used, and those 1 million values will never be used. So we've kind of wasted 1 million values. But again, because we chose 7 characters, we've got 3.5 trillion. So losing 1 million here and there actually isn't that much of a problem at all. But you could also say that the Zookeeper is also a single point of failure. So what we could do is we could have multiple.
Also my point, yes.
Instances of it. And you have to remember that the Zookeeper does not get that many read requests because, unlike the count cache, which every single time a web server wanted a number, it went to it, the web servers only go here to get its range of values. And then unless it finishes the range, it will not come back to that Zookeeper service. So this is a really robust solution that kind of scales really well.
I didn't hear the explanation of why, how, I didn't hear how it's still gonna work with the availability. Okay, like there is no problem with the number of requests this guy gonna process because, yeah, let's say we have, 1000 nodes. So 1000 nodes will come and create 1000 requests. Zookeeper will answer with the ranges, and then these nodes will keep going for some time. So load is not the problem. The problem is availability, and the problem with availability is exactly that you should maintain 2 states correctly, and how you're gonna do it with Zookeeper is this is not explained here. So this is completely not explained. So if it's instance 1 and instance 2, Like how we go? Okay, you now should do like this tricks with the modulo. So for example, this zookeeper now, I will run it with single digits, but you will get the idea. It works exactly the same with the ranges. So now this guy gonna issue, let's say, odd numbers. This zookeeper gonna issue only even numbers. Right, so this is one way how to ensure this, right? But you cannot upscale. You will not need most probably upscale, but if you need to add additional instance, what are you gonna do? Like there is no way you can add new instance here. So it's not completely scalable approach, and if you want to have more replicas of zookeeper, you cannot do it, right? How else you can do it? I don't know. You basically in a, you can do something like synchronous replication in this case, right? Because load and latency, I don't think they are the problem. Yeah, so you can do synchronous replication to bunch of zookeeper instances. It will slow down the system. And also, yeah, we cannot tolerate losing one of the replicas. We can theoretically still, yeah, so I don't think this is a very good solution, to be honest. I don't think so, because hardly it's hard to scale. There is problem and kind of hacks, and how a replication should work, how to make it consistent. So if this dies on halfway through, and how we're gonna change to this zookeeper and ensure it will not give something bad to our instances, so to omit duplication and stuff like that. I don't know. I don't think it's a very good solution. There is question: does MS in Czechia hire people with other stacks than .NET? Microsoft hires in an agnostic way to your language. It doesn't matter what you were writing before. If it's one of the like top known languages like JS, Python, Java, .NET, Go, whatever, it's okay. You will anyway end up in the project which has some specific language, and you're gonna learn this language. There is no other way.
The next step we can do then is to scale our databases. So again, here we can look at the classic, SQL, no SQL, ACID-based trade-off. So, you could make an argument. We could use, an SQL database like Postgres and then use sharding to handle the scale. But I think, maybe a slightly better approach might be to go with maybe column-orientated database like Cassandra, which could, really handle the scale that we're dealing with here. So typically I'd go with a no SQL kind of Cassandra approach here. And then to kind of reduce the load even more on the database, I'd also use maybe a distributed cache like Memcache or Redis. And here I'd store maybe the most popular short URLs so that the web servers would first check the cache to kind of reduce the load on the databases as well. So if we walk through an example, so let's say we've got a post request, so we're going to send a post request to the create URL endpoint. I'll come to the load balancer, which will then distribute it to the web servers. One of the web servers will then, if it doesn't have a range, it'll go to the zookeeper and get its range, and then it will generate the short URL from that number using the base62 encoding. The next step then will be to save the long URL and short URL in the database, and it could also store it in the distributed cache depending on what the caching logic is for the application. And then finally the web server will just respond to the user with the newly created short URL. And then
still topics of availability of cache and database are not covered. Basically you need both. Oh no, I think you need availability of database as well only. It doesn't matter depending on the approach, but sharding is not covered here, and replication is not covered yet.
Then for the GET request, what will happen is a GET request will come in with the short URL in the actual URL itself. The web server will first check the cache and see if it's in there. If it's not in there, well then it will retrieve it from the long URL from the database, and then it will simply redirect the user to the long URL. So really simple, but again, it's this kind of scalability issue that interviewers will really expect you to go deep on. And then finally, there's...
I completely don't like the approach with the zookeeper. I just want to know whether somebody pointed it or no. I really like the idea of zookeeper, computer short URL identifiers. No, it's not a good idea. Snowflake, guys, Snowflake. Well, database sequence would not have accomplished it because on a higher load or instead of zookeeper just put it a single instance of database that will do ranges. Yeah, this can be done, but again we have this problem with consistency and single point of failure. However, with the replication, well, yeah, some challenges are here. Okay, this is kind of a good idea, but instead of number it, yeah. So in this case, what is guy suggesting here? What is the name given to this diagram? Short URL shortener, I don't know. So we can put 62 instances of unique ID generators that are going to generate ID starting from specific symbol out of this 62. And this is actually a better approach than Zookeeper. I like it more. However, Snowflake is still the North Star here. I'm wondering what is the answer. But wouldn't this mean the state of large generated URL is stored in memory in the application servers? Okay. So
there may be some additional talking points which you may or may not be required to know. So one of them may be analytics. So what we could do is we could also maybe maintain counts for each of the URLs to determine which short URLs are most popular, and then cache them. And this kind of again can help us with the hotkey problem like that Twitter has. And then similarly, we also can store maybe IP address information to get location info, which can help us determine where to locate our caches to just, again, reduce that latency.
By the way, again, this system design is not covering how you're going to shard the storages, both database and cache. Also, it does not cover how we're going to ensure high availability and consistency.
Improve the overall performance. We can also introduce rate limiting, and so this can help prevent against DDoS attacks.
Oh, sorry, I missed one question in chat. Is this the beginning point of a web request? Does orchestration play a role at any point? Sorry, I didn't get the question. Beginning of web requests. Sorry, I didn't get the question, Sam, sorry.
Whereby users try and flood our servers with requests, kind of try and make them fail. And so rate limiting could be an interesting talking point. At our range theory, we are sequentially incrementing, and so therefore potentially we might want to add a random suffix to the short URL to prevent hackers being able to predict URLs, but then it will be making a trade-off between the length of the URL and the predictability. So that trade-off between length and security is one way of solving it. If you liked it, please like and subscribe. It helps the channel.
Okay, I see. So no Snowflake. I guess I would need to record my own video maybe. Let's see this one, but very quickly.
URL, and they are trying to significant period, and the common approach is to plan for it powered by some URLs to be shortened. First, we need to define the base endpoint will be JSON return 400 status code specified to get to the code. Next, let's talk price per second. Then we can assume that we will get at least 10 to 100,000 reads per second. In this case, we need to use a high performance statement, but we're not concerned in core like MongoDB or Ruby, but we're not concerned about it because we're not going to do bunch of joins or mix of characters to ensure uniqueness and non to generate shows on collisions. The other option is to, as example, use hashing here to generate a hash of a long URL and use part of it as the identifier and IDs, which is to use a database, but it might be predictable. And the other option is to come up with a custom algorithm and non-predictability. For example, there is a very simple way to avoid collisions. We can just generate all possible keys with 7 characters and store them in a database as keys, where each key is the generated URL and the value is boolean. If it's true, then this URL is already used, and if it's false, then we can use this URL to create a new map. So every time a user makes a request to generate a key, we can just find a URL from this database that is not currently in use and map it to the long URL that's in the
This is actually interesting approach. So we are pre-generating the all possible keys. And how do we then choose the key?
this URL is already used. There is a very simple way to avoid collisions. We can just generate all possible keys with 7 characters and store them in a database as keys, where each key is the generated URL and the value is boolean. If it's true, then this URL is already used, and if it's false, then we can use this URL to create a new map. So every time a user makes a request to generate a key, we can just find a URL from this database that is not currently in use and map it to the long URL that's in the request body. Now, do you think
I was trying to understand the flow from the starting point of making a ping to internet capable device either via HCI or automated controls. If you're talking about this guy that we designed over here, you're meaning this DNS stuff, how it's... This is actually not necessary part for usually system design. You can kind of assume that DNS is external, it's highly scalable, blah, 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 and you can just assume that your bunch of load balancers will get automatically balanced on its own. So yeah, right, because if you put only one load balancer, it's still single point of failure. At some point, under some certain loads, it will not have enough bandwidth at least.
we will use it?
I'm wondering how we're gonna search the like ID you can use in this approach.
SQL or NoSQL database here. Think of a scenario where two users ask to shorten their long URLs and they both got mapped to the same key from this database. In this case, the URL will be mapped to one of their requests and the other one will be broken. We can easily fix this by using SQL database because it comes with ACID properties, and we can create a transaction for each session here to make these steps in isolation, and we won't have to worry about such scenarios and issues in this case. So let's go with
Compare and search should work.
this approach and have a...
But I also don't like this approach because first you're pre-generating. What is the algorithm for choosing the free one? Like, would you just... Okay, actually in database you can kind of do through the var statement. So you're gonna... It's log n for new. Okay, might actually work. It might actually work. But actually, it will work badly. I will, yeah, it's a good catch. So, let's say that we are doing the approach of this guy. IG accessing Facebook to login, register, send friend request, etc. Yeah, I see. No, actually, I don't think. No, I'm not pointing this one. It's not the full traversal. Like if you want to go through the full traversal, we should check this PIP stack and go level by level. So let's see the problem with this approach. This is very interesting, but I would assume, because it's not explained, I would assume that the approach here is to do something like this. So select from IDs or whatever the table is called, where IDs URL, no, let's say free or not occupied, whatever, equals to true. This is the statement. Okay, and now, well, it depends, right? Good catch. It depends how SQL will arrange it because it does not guarantee order, right? If we are doing order by, then it's a problem here. It's a problem here because it will always, like, let's say 1000 requests per second even, and all of these 1000 requests per second try to write to exactly these last three guys. So I cannot tell at the moment, you know what I mean? Because let's say we have 1, 2, 3, 4, 5, 6. Let's say we have these occupied already, so they are false, and these three are true. The problem is that order of this SQL statement is not guaranteed because we don't use order by keywords. So the arrangement of these rows can be any, but it still might have high probability of some specific order, because let's say the database reads it from the memory leaf in the disk, right? So it can be that this part, for example, is always ordered at exactly same way. So we're gonna just get and also it should be limit 1. So we're gonna get just first one, and the problem is that in case this return value is somehow ordered, our 1000 or 1 million or whatever requests per second gonna try to write to exactly this particular row, and we even cannot calculate exactly the probability of this because it depends completely on the internals of the database, which is very bad. Other approach to have deterministic one is to use ordering, but ordering will make it worse, because if these guys are ordered and we're just gonna get the next true, the next free one, we for sure can say that all requests will try to write to this guy, and we will have a lot of collisions, a lot of optimistic concurrency errors, stuff like that. So without order by, it's not guaranteed to be mapped to the same one. It has some probability. With order by, it is guaranteed. So bad approach.
Scenario
I
where
don't like
two
it.
user ask properties and this approach and have another keys database, which is, let's say, Postgres database or MySQL database that stores the keys and Boolean values in front of them. Now this system obviously won't be able to handle the traffic of 1000 URLs per second. So let's go with this approach and the transaction other stores the keys and Boolean values in front of them. Now this system obviously won't be able to handle the traffic of 1000 URLs per second, and to make this more scalable, first we need to introduce a caching layer. We'll use a caching layer to cache popular URLs for quick access, somewhere in an in-memory cache with tools like Redis, and given that some URLs might be accessed much more frequently than others, we need an eviction policy that prioritizes frequently accessed items. So the two suitable caching eviction policies for this scenario are the LRU and TTL cache. With the LRU cache and 3, and once the automatically refreshing the cache manager. That key-based sharding to distribute the URL records across multiple shards evenly. Let's say we distribute these to 3 shards as the number of URLs grows in our system, and we can also implement master-slave replication shards evenly.
But what is the sharding key you're gonna use?
Let's say we distribute these to 3 shards, and each shard will approximately have 1 trillion distribute unique URLs with our string strategies here. Considering that we have 3.5 trillion unique URLs with our 7-character set, we can use key-based sharding to distribute the URL records across multiple shards evenly. Let's say we distribute these to 3 shards, and each shard will approximately have 1 trillion URLs. This will ensure scalability as the number of URLs grows in our system. And we can also implement master-slave replications within each shard to ensure high availability and fault tolerance. And this setup allows for quick failover and recovery in case of node failures. So for each shard we will have attacks. We can implement rate limit.
Okay, security. Okay, also not that good approach. I don't like it. Okay, maybe let's look quickly one more, and yeah, if nothing good, I gonna implement it. Okay, maybe we can, let's actually review others later on. This is gonna be interesting stuff to do, like, and to evaluate our system design as well. For now, I think we're done. We are streaming 2 and more than 2 hours already. So thank you for being with me, guys. Thank you. It was a nice one. It was really nice one. And yeah, next session we're gonna continue with LeetCode, maybe some new insights from interviews, I don't know, and system design review for other system designs. We're gonna go through all of them and check and compare with our system design that we just created here. It was me, Andriy. Thank you for being with me, and see you.